me share my screen. And okay, let's start with a picture of the universe that I suspect you are all very familiar with, which is the idea that putting all of our best cosmological data together, we come up with a picture of the universe that is 5% made of matter that we are more familiar with, that we can study in our lab. About 25, 26, 27% dark matter, which obviously what you have been focusing on so far in this school, and 68 to 70% dark energy, which is the focus of the next of my lectures. And what we're really going to focus on is how difficult it actually is to incorporate this substance or this component of our universe into our standard models of gravity and quantum mechanics. I think there's no real serious debate about this picture of the universe at this point in time. The issues are really how to fit these observations into our theories in a way that makes sense. And to set up the terminology that we're going to use, dark energy is in the broadest sense just the name that we give to whatever substance, fields, modifications of standard physics that solves the problems of this component. So we're going to get into what the cosmological constant problems are in a minute. So dark energy is just sort of whatever new physics you have to add in to explain these observations in the context of our standard models of physics. Some people prefer dark energy only for like a field that drives the accelerated expansion of the universe, that reproduces all of the observed phenomenology. So there's a little bit of tension there in the language, but I'm going to use it in the sort of broad sense of covering all possible kind of solutions to the problems. So the real conclusive evidence for the presence of dark energy or a cosmological constant component in our universe comes from, again, as I suspect you probably know, from observations of high redshift supernova. So these are type 1a supernova. So they are stars, white dwarf stars that explode when they reach the Chandrasekhar mass threshold, and the balance between sort of gravity pulling stuff in towards the center of the star and the thermal pressure pushing stuff out becomes unstable, and the whole star has a kind of massive thermonuclear explosion. And so they all, to a first approximation, they all shine with the same brightness wherever and whenever they occur in our universe. And so you can use them as a standard candle. You can say the ones that are dimmer are further away and the ones that are brighter are closer. Now, I'm sort of deliberately showing you an old picture of supernova data here because this, I don't want to get sidetracked into talking about the current Hubble tension, which obviously also comes from exactly this issue of trying to reconstruct the expansion history of the universe, or at least in part, comes from trying to reconstruct the expansion history of the universe with supernova. So this is actually what the data look like when these two pioneering studies, the Supernova Cosmology Project and the High-Z Supernova Search, really did these first observations and kind of showed definitively that we don't live in a universe that is entirely dominated by matter. So what is shown here on this plot is redshift on the horizontal axis, so how distant galaxies are moving away from us, or equivalently how far away they are, and the relative brightness of the supernova on the vertical axis. Okay, so the main plot, the colored version, is a zoomed in plot of the high redshift part of the bigger plot. Hopefully that's clear. With the color coding being an accelerating and decelerating universe. So the first thing to say is that we do live on the edge of, sort of on the tipping, very close to the tipping point between an accelerating universe and a decelerating universe. And that's kind of in itself quite an interesting observation. We don't live well in one or the other, and that's sort of part of the problems of the cosmological constant problem. Why do we live in this particular sort of special universe? And I'm also showing this plot because you might have heard some discussion about, like, that there's some debate about whether these observations really shows that the expansion of the universe was accelerating or not. And I think you can sort of see by looking at this image that this maybe not, at least by eye, it's not totally convincing. But that, I think that's really underselling what these observations do. And I should say, obviously, this is old data, so that we have many more observations of supernova than this plot now. But what the supernova observations really do is they really break the degeneracies in this plot. So this is a plot of the fraction of our universe that is made up of matter, so omega matter on the horizontal axis, and the fraction of our universe that is made up of something that looks like a cosmological constant on the vertical axis. And so if those two things add up to 1, you live on the black dashed line that runs sort of diagonally through the middle of this figure. The data from the CMB is the degenerate sort of green line through the middle here. So you can see without, ignoring BIO for the moment, without the supernova data, we could have lived, it still would have been possible for us to live in a universe that was entirely dominated by matter. And I think that's the key thing that the supernova observations tell us, really, is that is not a viable cosmology. That doesn't, a universe entirely dominated by matter doesn't match our observations anymore. And actually we end up putting now all of our cosmological data together. We end up zooming in on this point, as we said earlier, that the universe is about 30% matter and dark matter, and about 70% cosmological constant or dark energy today. Okay, so that's important. And I think sort of key thing that often gets misunderstood about what what the supernova data really convincingly tells you. It's probably also worth mentioning that despite the fact that the supernova data were really the key thing in convincing everybody that this is the correct picture of the universe, actually there were already a number of indicators that you couldn't have a universe that was entirely dominated by matter, and in fact you needed something that looks like a cosmological constant. For example, without a cosmological constant, if you try and calculate the age of the universe and you try and compare that with the age of the oldest stars, there's maybe a tension there that the universe doesn't look old enough for the stars to live in it. There are also issues with, for example, predicting getting the number density of galaxies right, or kind of trying to explain the observed flatness of the universe. And all of these things were known before these kind of key observations of type 1a supernovae. Okay. So let's come back to me for a minute. The other, especially in the context of this school, the other kind of introductory point that I wanted to make is there is a real difference between where we are in our study of dark energy or cosmological constant problem, and where we are in our study of dark matter. I think you will know better than me, but I think it's fair to say that at the current time, we have a number of very good candidates for what dark matter might be. There's still work to do on understanding those theories, of course, but we've got a number of really good viable candidates that would sort of make sense in our theory of physics. Excuse me. And really kind of currently the challenge is to experimentally or observationally identify which of those options our universe prefers. When it comes to dark energy or the cosmological constant, I think we're really in a different situation. in the sense that there's no, I think it's fair to say, there's no widely accepted solution to the cosmological constant problem. There are different approaches, different attempts, but they all sort of struggle. Either they just are in tension with some other observation that we've made, or at least under pressure from some other observations, or they excuse me, or they require us to do something that we might be slightly uncomfortable with to our kind of fundamental physical principles. Maybe we have to give up locality, for example. Maybe we have to give up that physics comes from an action principle. There are all sorts of kind of widely varying sort of proposals for solving the problems that I promise, going to tell you about in more detail in a few minutes. And you know, people try to solve this within string theory. They try to solve it, as we'll see, by modifying our theory of gravity. It's really this field is really at a different point in its evolution compared to dark matter, in that we're really still understanding how to build sensible theories of a cosmological constant or dark energy theory. Okay, so that's one side of what I've been asked to talk about. The other side, of course, is to talk about extensions to gravity or modifications of gravity, and we'll see why those two things are so well tied, or so closely tied together. But just to say from the beginning that it's really, really hard to modify gravity, and that's because we've tested it so well. So what this is a plot of searches for. So this is obviously only one possible modification of gravity, but it's kind of a simple one that you kind of might want to think about first. And that's the idea that maybe there's another force, another fifth force in our universe. This kind of behavior can be got by matter particles exchanging a scalar field to mediate the force. If that scalar field has a mass m, or m sub phi, then we get an exponential suppression, as you can see here. Otherwise, the potential interaction between two masses will go like those two masses. There's a 1/r scaling with distance, as you might expect, and then some coupling constant, which here we're scaling relative to gravity. So alpha is the relative strength of that force compared to gravity. And so what these two plots show you are the constraints on this kind of force. On the left-hand plot, as the laboratory experiments, the laboratory constraints on this type of interaction, and on the right-hand side, the solar system constraints on this type of interaction. Because obviously, if you modify gravity, you modify the motion of planets and moons and satellites, and that can be tested because we have been studying how objects move in our solar system for a very long time. So what is on the vertical axis here is this parameter alpha, the strength of the interaction compared to gravity, or strength of our new interaction compared to gravity. And on the horizontal axis, the Compton wavelength of the field, so 1/the mass scale here, or kind of roughly equivalently the distance scale of the measurements. And so you can see, obviously, our ability to study this falls off at short distances. So the constraints are not very good at very, very short distances. But even at the sort of millimeter and below scale, we're constraining alpha to be smaller than 1, maybe 2 orders of magnitude here, smaller than 1. And on solar system scales, we're constraining it extremely well. Excuse me. Oh, sorry. Hi. I'm in the middle of something. Can we leave it for the moment? Thank you. Sorry, somebody just came in to empty my bin in my office. I'm not normally in this early. I didn't know that was going to happen. Yeah. These most constraining ones that are marked LLR are the lunar laser ranging measurements. So really precise measurements of how the moon is moving in the Earth-Sun system, which is a very, very good test of gravity. So that's kind of the thing that we're going to keep coming up against, and that we're going to that I'm going to come and talk about a lot more. Which is just that it's really, really hard to modify gravity. You have a lot of tests that you need to pass in order to do it. And to some extent, that's why we don't have good, lots of good theories for what dark energy or cosmological constant might be. It's just that we just keep running into the wealth of observational data that we have.
Can I ask a quick question, please?
Yeah, of course.
Thank you. On the left plot, what is that dark energy scale vertical line?
Right. So that's sorry, I'm clicking on the wrong thing. If we take our observations of this omega lambda and we say, okay, this is a cosmological constant, what is the equivalent energy scale to that? We get an energy scale that's about 10 to the minus 3 electron volts. And then if you just convert that into a distance scale, you get roughly this point here on the left-hand plot. So that's where that energy scale would be if we turn it into a distance.
Okay, so our observations basically tell us about what the mass of the scalar particle has to be if we were going to describe dark energy with a physics force.
Yeah, so I should say that obviously what I'm showing you here is an attractive force. So that in itself is not going to drive an accelerated expansion of the universe. And maybe this is worth saying again, because we're not because we're so early in the stage of developing good theories here. One of the things that we're doing is we're really just at the point of asking, well, what can there be any new physics associated with the energy scales in our problem? So that's why this is interesting. It's just like, this is the energy scale or the equivalent distance scale associated with this kind of thing that we don't quite understand. Let's have a look and see if there's anything interesting going on at that scale. Is there any new physics associated with it? Does that make sense?
Yes, it does. Oh, I think the mic died. Okay.
Yeah, and that's kind of actually that touches on something else, which is either like a massive kind of issue for these theories, or kind of something that's a really exciting opportunity here, which is just, right, we're talking about something that is affecting the universe on the very, very largest scales, right, on enormous distance scales, way bigger than I'm plotting here, but it's also associated with a sub-millimeter distance scale, right? And so where to put your new physics to solve this problem, how to get something that affects that big hierarchy of scales is another part of the problem that we're dealing with here. Okay. Oh, sorry, I wanted to stop sharing. Right. Okay, so that's sort of the setup, sort of to introduce you to kind of what we're talking about in these two lectures. I also want to say that kind of because this is a sort of short course, I had to make a decision about, do I try and be really comprehensive and give you kind of, or do I kind of try and be a bit more narrow, give you a little bit more depth on fewer things. And the way that I've gone is I've decided basically that I'm going to use simple scalar field models throughout these lectures, both as my dark energy and as my modifications of gravity. And that's going to allow us to see a little bit of the physics come through and kind of how the calculations work. Obviously, there's much more going on in this field than I have time to talk to you about. I'll try and kind of hint or indicate what that looks like as we go along. That was the choice I made in putting these lectures together. It was to stick to scalar fields. But again, if you have any questions about what those extensions look like or what other alternatives are out there, then do definitely ask questions. Okay, so that's my introduction. We're going to go on now to talk a little bit about firstly about general relativity and then to build up to talking about the cosmological constant problem. But I guess at this point, are there any questions or any issues that I should know about before we go on?
No. On that plot you showed us, or the last plot you showed, on the right side, why it's so hard to constrain like in 0 or one order of magnitude in this scale?
Sorry.
There's this large blank area.
The plot back up for you.
Yes.
Oh, hang on. Sorry, this one.
Yeah.
So why does it fall off at larger distance scales?
Yeah, for like 0 order or 2 distance scales. Like seems like there will be like this.
Sorry, maybe I'm not quite hearing you properly. Could you just ask the question again?
Okay, no, my question is just to know why it's so hard, like to constrain this small scale area.
This area on the right hand.
Yeah, this one. Yeah.
Right. Yeah, it's a combination of what probes you have and how simple or complicated the physics is that you're using. Now, so I think maybe it's actually the way to answer your question is, in fact, so you can see what's up on the top left here is these are laboratory constraints and geophysical measurements, so kind of studies of the Earth. And obviously there we have very, very good control over our experiment. We can repeat them. We have kind of laboratory experiments are always the best for kind of being able to characterize your systematics and understand them. So I think actually the way I would look at this plot is, why on earth are these solar system constraints so good? Why are they so much better than we can do in the lab? And that is, I think, largely due to two things. Firstly, actually, that the physics is is comparatively simple, that you're studying to first order approximation anyway, the lunar laser ranging constraints, you're studying how the moon moves around the Earth, and that ought to be governed by really quite simple physics. Okay, then you have to include the influence of the sun and the other planets in the solar system. I'm not saying it's trivial, but it's still quite simple linear physics, and we've been able to make those measurements for a very long time now. And so we've got a long integration time as well. And I think those two things together allow us, and again, we've been observing planetary orbits for a very, very long time. So I think it's actually that the physics of the solar system is comparatively simple and clean. And then just kind of integration time that means that these constraints are so good. Any other questions at this point?
I don't see any. Okay,
great. So then I am going to switch to my document cam. I'll share my screen again. Okay, so I'm going to give the lectures a little bit a mix of slides and my document cam so we can write and kind of see how the equations work out. I find it kind of nicer than putting everything on the slide. So the next thing I want to talk about is another part of the reason why this game is so hard, which is that general relativity actually turns out to be an incredibly special and unique theory. It's obviously our current best theory of gravity, and we can think of it as the theory of a curved space-time manifold, or we can think of it as a theory of a massless spin 2 field, which is mediating a gravitational interaction. And as long as we don't want to go to super high energies, those two pictures agree with one another. But what I think is is so surprising is that once you sort of set out kind of the principles that you want your physics to follow, sort of general relativity is almost unavoidable as the theory. Sorry, let me see if I can focus that a bit better. There we go. So, for example, one way to see why general relativity is special is Lovelock's theorem, which says if we think we are interested in physics in 4 dimensions, and if we think that physics should come from an action principle, and if we think gravity is the sort of fundamental object in our theory of gravity is a metric, this is our G mu nu here, and if we think our equations of motion should be second order in time derivatives, and we would like to insist on that because otherwise we get ghost instabilities, or we need more initial data to explain our system than we think we should. So we get extra degrees of freedom, maybe they're unstable. So all of those things sound like pretty reasonable things to request. Equivalently to thinking about this as our metric tensor, we can think of it as our spin 2 field. If we start with those very reasonable requests for our theory, then the only possible equations of motion that we can get have this form, okay, which potentially looks already familiar to you. So alpha here and lambda are unknown constants at this point. This is little g, just to make the notation clear, little g is the determinant of our metric. This is the Ricci tensor and the Ricci scalar here. So that's already kind of super restrictive in terms of what we can do, right? Essentially, the only freedoms we have here are two constants. And you can ask, okay, well, if this is the only possible second order equation of motion I can get, what's the simplest action principle that I can have that gives me that? And you get this action here, which looks as hopefully you'll notice, like the Einstein-Hilbert action minus something that will look very much like a cosmological constant.
Can I ask a question?
Sure.
Thanks. I believe you said that we can think about our metric as a spin 2 field. Could you say a little more about that, please? Oh, okay. I could say a lot more about that, but so what's the best way to say it? Well, so there are lots of interesting lots of interesting history here, but so what I've shown you here is one way of seeing that general relativity is special. Another way you can see that is to say, well, I want gravity to be mediated by a spin 2 field, and then try and construct an action describing that spin 2 field, and insist that it has to be Lorentz invariant and free of ghosts and free of instabilities and things like that. And actually in that way, again, you get to basically that the only theory you're allowed to have is general relativity. So it's really interesting, I think, that in the history of physics that Einstein kind of was able to identify GR coming from this very classical differential geometry approach. If that hadn't happened, we probably would have constructed it from a field theory approach as well, thinking about what happens, what the action of a spin 2 field has to look like, but that might have come kind of in the 50s and 60s rather than 100 years ago. Does that, I don't know, I mean, there's a lot more to say, obviously, but does that sort of help a little bit at this point? That does help, yeah, thank you.
There's also a question in the chat.
Okay, sorry, thank you for pointing that out. Can you tell me what it's, sorry, I don't know how I say
that. Is there any reason why we are considering matter less? Field equations here.
So excellent, right, next slide.
we are gonna, yeah, no. So this, what I've shown here is, of course, a purely gravitational theory. And okay, so now I can see, sorry, I didn't see where it was, where the chat. Yeah, so this is purely gravity. We do get more freedom when we include matter as well, which is exactly what we're now gonna talk about. And here again, you have some more choices. And possibly this is where you might want to think, this is one place again where you might want to think about whether the choices we typically make are, you know, are things you're willing to give up. But what we generally choose here, so this is schematically now, this is the same action we had before, and I've just included a matter Lagrangian, which is going to depend on our metric and on just, this is just a placeholder for some matter fields here. And what we're going to assume is that these matter fields interact with the metric degree of freedom. So they don't, this is the relevant thing for writing down the relevant quantity for writing down the matter Lagrangian, and that all of our fields interact with gravity in the same way. All of our matter fields interact with the gravity in the same way. So that's known as universal coupling. You know, that Newton's constant is the same no matter what type of matter we use to make a measurement of it. And then putting that together, we get the Einstein equations, and our two unknown constants, which were alpha and lambda, then become the cosmological constant and Newton's constant, or the Planck scale. And we can fix those two unknown constants with measurements. Okay, so all that happens going from here to here is we do a variation of our matter Lagrangian with respect to the metric. That gives us an energy momentum tensor. And then it turns out that that the Bianchi identities of general relativity, so the symmetries of our underlying, the symmetries present in the gravitational sector kind of enforce us to have conservation of matter in this way. Okay, so that sort of gives you again a little bit of an idea of why it is that that it's not straightforward to modify our theory of gravity, at least. We can do things if we go back to the pieces that we had to put in to get general relativity out. We could give up the idea that we live in 4 dimensions, which you know would certainly maybe go in a string theory direction, perhaps. We could give up starting from an action principle. Maybe we can live with ghosts in our theory and we don't need to insist on second order equations of motion. Or maybe, you know, maybe matter doesn't couple universally to gravity. The other possibility is, sorry, going back to my first slide again, is maybe that this metric tensor or this spin 2 field is not the only field in the gravity sector. And that's one of the that's kind of one of the modifications of gravity that I'm going to focus on, because it's a modification that doesn't really require us to give up the things that feel kind of fundamental, right? We can I would, you know, I'm not yet ready to stand up in front of you and say, oh, physics no longer comes from an action principle, right? However, maybe I'm prepared to say, maybe gravity is not just one single field, maybe there are more fields in the gravitational sector. So that's kind of the way in which we modify gravity that we're going to focus on. Okay, so that was setting up, obviously, our standard picture of general relativity. So I'm going to move on and quickly just talk about our standard picture of cosmology as well, but maybe I can also pause and ask if there are any other questions at this point.
Okay, cool. So we take our theory of general relativity and we say that we're happy with that for the moment as our theory of gravity. And we're going to impose cosmological principles of homogeneity and isotropy. I'm going to say for the moment that our universe is completely uniform. And what I'm interested in is the evolution of the scale factor with time. Okay, so our scale factor in our FRW metric is A. We're going to assume that matter is a perfect fluid, and then these are the Friedmann equations that we get, and our conservation of matter becomes this continuity equation here. Okay, now although I've written it in for completeness, I'm actually going to ignore the curvature of the universe for the rest of these lectures and set that to be 0, which is kind of currently in agreement with all of our observations. Okay, so this is our cosmological constant. This is the term that is, well, going to help us explain our observational data, but also cause us all of our problems. So what does it do? Well, if oh, I haven't, sorry, I should have said that obviously the Hubble constant is A dot over A. Now, if we have a universe that's entirely dominated by a cosmological constant, so lambda is really a constant, then our Friedmann equation tells us that A dot over A has to be a constant. And we're going to get, that's where our exponential expansion is going to come from. So from here, we get that our scale factor goes like e to the power of square root lambda over 3 times t. Okay, so purely cosmological constant domination gives us exponential expansion of the scale factor with time. But we can also say, well, okay, that's not the only term on the right hand side of our equations. I've got this term, this rho term here. Can that mimic this expansion? Are these really kind of separate terms? Or, you know, is it possible for something in my matter sector to look like a cosmological constant? Because then I'm going to have problems differentiating between them. Oh, okay, sorry, I thought I had this right now. So if we were to do that, these are our two equations. So we want to ask, what does it take for matter to mimic a cosmological constant? So if we want to reproduce all of the effects of lambda, then we have to have that 8 pi g rho over 3 is equal to lambda over 3. So these two terms are equal. We also need the second Friedmann equation to hold. So we need 4 pi, sorry, I've missed a minus sign there, haven't I? 4 pi g over 3 rho plus 3p to be equal to lambda over 3. And we can also see from this equation that if our rho is mimicking all of the cosmological constant, then rho had better be a constant as well. So for our continuity equation to be satisfied, so for rho dot to equal 0, oh, why has that disappeared? Come back. Oh, hold on, sorry about this. I think that's just a bad connection. Okay, there we go, came back. Can somebody just tell me that you can still see that? Yeah, excellent. Okay. Cool. Right, so we were saying, what does matter need to do to mimic the cosmological constant? So we have rho as a constant, so we also need that for our continuity equation to be satisfied, we need rho is equal to minus p. And then we can rearrange this. and see that we also need that rho is equal to minus lambda over 8 pi g. And these two things together actually do turn out to satisfy all of the equations. So it's perfectly possible for matter to mimic a cosmological constant. So maybe this distinction between the two terms is not, not, or this is kind of where the problems are going to come from. How do we distinguish between an effective cosmological constant that comes from matter and a true cosmological constant, if you like, in our equation summation? But of course, this is not necessarily a type of matter that we're particularly used to dealing with an equation of state W equals -1. And again, you hear people talking about negative pressures in this context. I think, honestly, all that means is that probably a perfect fluid description is not a very useful way of talking about matter when it comes to matter that mimics a cosmological constant. And we'll see in a minute or in a few minutes kind of the type of matter that actually can give you this kind of behavior. Okay, so that's the first point, is that matter can look like a cosmological constant, and it's not a priori easy to distinguish between the two. And that is where the problems start coming in. So, because the cosmological constant is a constant and it's the same at all points in space and all points in time. So again, you might ask, well, if I truly want to mimic a cosmological constant, what things in my matter sector are the same at all points in space and all points in time? And it turns out that the object that has that property, that is constant across space and time, is the energy momentum tensor of the vacuum. Now, another way to see that is that the vacuum has to be Lorentz invariant. If we want an object that has the same index structure as our energy momentum tensor, then the only object that we have, or the simplest object we have rather, is our metric tensor, and that because it has to be constant, all we're able to do is introduce a constant in front of that, so rho back. So this is our vacuum energy momentum tensor, and if we were to put this into our Einstein equations, we would find that indeed this looks exactly like a cosmological constant. I'm sorry, I think there's a slight loose connection at my end. I will try and fix that for tomorrow.
And I have a question.
Yeah, sure.
Isn't it possible for the vacuum itself to go through some kind of evolution in some models?
You guys are all way ahead of me. Yeah, I'm going to come to this in just a second.
Okay,
I think, in fact, this is probably the next point that I was going to make.
Okay.
Yeah. So yeah, exactly. So the question is then, what is this quantity rho back? If it's truly the property of the vacuum, then we think it should be constant. But as you've just pointed out, it might be constant for almost all time, but maybe not entirely. So to see that, as I said, we're going to stick with simple scalar field models. So this is my action for a scalar field. So
can I ask a question?
Yeah, sure.
So in the previous calculation, the way we wrote the equation, it seemed like the density of the cosmological constant is negative and the pressure is positive. But typically I've seen it the other way around, like a positive energy density and a negative pressure. So I'm a bit confused.
Right.
On the convention here.
Yeah, well spotted. Partly this is just an issue of sign conventions. And partly actually that I didn't tell you that lambda was the lambda I'd written in that equation was necessarily a positive quantity. So to fix kind of what that looks like, what that object looks like, you would then go away and match it to your observations and find, you know, in fact, I believe with the way I've written the signs then that lambda turns out to be negative and you still do get a positive right, I'm sorry, that's maybe not the clearest way I could have written that.
Okay, I see. Thank you.
Right, so this is our scalar field, and we're giving it just a canonical kinetic term and some potential, which for the moment that I'm not going to specify. So then if we were to go away and compute the energy momentum tensor for that, that's going to be some function of derivatives of the field and of the potential. And then we ask, well, I want to know what the vacuum contribution of my scalar field is. Now, if it's in vacuum, I shouldn't have any gradients of my scalar field because the vacuum should be the same everywhere. So all dependence on gradients of the field should disappear. And in order for that to happen and the equations of motion to be satisfied, my field had better be living at the minimum of its potential everywhere. So this then is the structure that you get for the vacuum energy of your scalar field. We're just talking classically for the moment. So that this is just the minimum of the potential. But exactly as has been pointed out, that actually can evolve as the universe evolves. And the kind of classic example of this is if our universe goes through some spontaneous symmetry breaking behavior. So maybe in the early universe, the potential looks like this. And again, I haven't drawn this properly, but I'm kind of imagining that my field is sat at 0 at the minimum of this potential. And then as time goes on, we undergo a symmetry breaking transition. The potential evolves, and now the field is sat down here at some other value, but also importantly, some different amount of V min, if it be evaluated at the minimum. So again, this is why we see this is again another one of the reasons why the cosmological constant problem is difficult to solve, which is okay, and we're only talking classically at the moment. We haven't yet got to the complications of making this a quantum theory. Is well, which of these values do I pick to match the constant that I observe? If I think my observed cosmological constant is coming from the value of my scalar potential, which of these ones do I match? Well, maybe I probably want to match the late universe one, but why is that the right answer? It's not obvious from kind of any sort of first principles. And this is not a hypothetical. We know that the universe has gone through at least 2 phase transitions in its history, like the electroweak and the QCD phase transitions, potentially even more in the early universe. If you think maybe there's some gut theory, or depending on what you think happens at the end of inflation. And so the potential problems of fine-tuning the cosmological constant are not just that you have to fine-tune it to match our observations once, but you kind of have to explain how that comes about from this kind of from this changing value through the history of the universe. Okay, so that's the classical way, the classical cosmological constant problem. Things get even more complicated and more problematic as we start to think about this as a quantum theory. Okay. So this is a calculation that you have potentially seen, because this is a very, very common way for the cosmological constant problem to be presented, which is to say, I am going to imagine that my universe is actually a set of simple harmonic oscillators, or rather simply oscillating scalar fields. So this is just a Fourier decomposition of the scalar field we've been talking about. Okay. And then to say from that, I'm going to compute what is the vacuum energy density of that and what is the vacuum pressure. Okay, so I can take this, I can compute my energy momentum tensor for these fields. I can ask what that looks like in the vacuum, and these are the two expressions you would get. Okay, so that goes like, so omega here is the frequency as a function of k. And then the typical calculation is to say, well, at this point I have a problem because both of these integrals diverge, right? This is scaling for at least for large k, like a power of k. I've got the integral of 3k over 3k's here. That is definitely not a convergent integral if I integrate all the way up to infinity. So how do I regulate that? And the common approach, the calculation that often gets taught at undergraduate level is just to say, well, I'm going to put a hard cutoff on these integrals. I'm going to say that these are integrals up to some k scale, which I'm suggestively going to call lambda, except I don't do that in my calculation, so I'm going to call it m, and write out what these integrals look like if I cut them off at some high scale. That certainly solves the problem of them blowing up, but what you find is that these are your answers, okay? And that's a problem because if we take the ratio of those, we find that W is equal to 1/3. So this doesn't look like a cosmological constant at all. Previously, we said that we had to have rho equals minus p, or so for a cosmological constant, we need W equals -1. So this calculation of what we thought was going to be the vacuum energy seems to have given us something that in fact has the equation of state of radiation. So what is the problem here? Why is this calculation that we've all been taught, where does it go wrong? And the reason that it goes wrong and that you shouldn't trust this answer is that a hard cutoff is not Lorentz invariant. We're asking about property of the vacuum. We really should be looking for a Lorentz invariant calculation to give us a Lorentz invariant answer. And sticking one hard energy scale into our theory breaks that. Okay, so which at this point we shouldn't think of this as kind of some flaw in our understanding or something that's gone very wrong in physics. What we should see it as is the fact that we've done the calculation wrong and we should be more careful. And I want to put this out because this point seems to get rediscovered every once in a while, sometimes by people who perhaps should know better, that maybe there isn't a cosmological constant problem at all, because if you put a hard cutoff on these integrals, you don't get a cosmological constant. But that's because we're doing the calculation wrong. So how can you do this calculation properly, keeping Lorentz invariance? Well, there are, as always with ways of regularizing divergences in quantum mechanics, there are different choices you can make. But one that will work for us is dimensional regularization, which if you haven't seen, I'm not going to explain at this point, but just believe me that it's a Lorentz invariant way of regularizing these divergences, where we set the dimension of our universe to be not necessarily 4, in which case we can solve the integrals, we get these answers, and the divergences are wrapped up in these gamma functions, because when d equals 4, they blow up. But if we subtract the divergences from these integrals, sorry, if we subtract the poles in these gamma functions, then we do indeed find, as you can see, that the only difference between these two expressions is the minus sign here, and we do in fact recover that W is equal to -1. So that is to say that we do get a consistent picture of physics. If we try and calculate a vacuum energy, we do find something with an equation of state equal to -1.
We have to be careful about how we do it. But if we do that, so yeah, I should have said this is a regularization scale in this problem, and M is just the mass of our scalar field. And if we do that, if we do subtract the pole, then this is the expression that we get for our energy density of the vacuum. And what we can see is that it scales as the fourth power of the mass of our scalar field. To a first approximation, I mean, obviously our universe is filled with many more things than just simple oscillating scalar fields. But again, if you were to do the calculation for fermionic theory, you would find a similar expression that rho does scale like the fourth power of the masses of your particles. And so the amount of vacuum energy in the universe scales as the mass of the heaviest particle that you want to put in your theory, which is a problem when our observed lambda is roughly 10 to the minus 3 electron volts to the fourth power. So that would all be perfectly fine and consistent if the heaviest particle we knew of had a mass that was 10 to the minus 3 electron volts. But unfortunately, that's the mass, sort of the mass scale of the neutrinos. And we know that there are definitely particles with masses heavier than that in our universe. So that's kind of fundamentally the cosmological constant problem or we've seen two aspects of the cosmological constant problem. How do you cope with the fact that the vacuum energy density evolves during the evolution of the universe? And how do you cope with the fact that the observed value is so much less than the one you would predict for the vacuum energy density, given a universe with the matter that we know is present? And I think it's worth saying as well that this is not a problem of new physics. This is a problem of the existing physics we have, right? We don't need to be speculating about super heavy particles or UV completions for this to be a problem. That the mass scale of the heaviest particle in our theory is bigger than what we observe this constant to be. So that is the cosmological constant problem. And that is largely the motivation for trying to go beyond this, going beyond simply general relativity plus the matter that we have in our universe, or that we've seen. So there's two approaches then that you can take. One is, as we've sort of been talking about, is to say, maybe I'm just going to add some more matter, different types of matter, some unusual types of matter into. Yeah.
I quite didn't get the part of the phase transition. Would you mind explaining it quickly?
The issue of the phase. So yeah, of course. So the issue there is, well, I guess maybe we can talk about it at this point in light of the two pieces together. So we have from the matter in our universe, we have two contributions that look like a cosmological constant. One is what we've just been talking about the vacuum energy density, the vacuum energy density that comes from quantum fluctuations or oscillations of our scalar field. That's the one that scales like the fourth power of the highest mass in the theory. And the other contribution is a classical one that you get in addition, which comes from, if your field is moving in a potential, will just be the height of the potential. That also looks like a cosmological constant. So we've got these two matter contributions, plus potentially a bare cosmological constant that we have to match to be the observed cosmological constant. So you can do that fine tuning today and just say, okay, well, those things have to sum up to whatever I observe. And I'm just going to accept that I have to fine tune it to match our observations. But then you have to explain why was that the right choice? Why wasn't it right to choose that the cosmological constant was matched the value of our potential before the phase transition, where that contribution had a different value. And so if you if you believe that our observations are truly described by a constant, then you have to explain why that fine-tuning is done today, which is kind of picking today out as a special time in the history of the universe to do that tuning.
Yeah, but why do we know there wasn't this transition for this theory, for this scalar field?
Right. But if we're allowing things to evolve, then we can do all sorts of things. So if we're putting a new scalar field in, we don't have to assume that it goes through a phase transition, but there's one scalar field that we know we have to put in our theory, which is the Higgs. And we know that that goes through electroweak symmetry breaking, and the contribution of the Higgs to the vacuum energy is different before and after that phase transition. So that's unavoidable. It's not something that we can get away from.
Okay, I see. Thank you.
No worries. Any other questions?
Not for the moment.
Okay, so hopefully I have at this point convinced you that it could be interesting to try and think about extending our theory of gravity. So this is, at least in the context of what we're going to be talking about, motivated by trying to find a solution to the cosmological constant problem. People also think about modifying gravity because they're interested in trying to come up with a UV complete theory of gravity. It's not obvious that those two motivations give you the same modifications. As we've said, the cosmological constant problem is actually a very low energy, large distance problem, whereas UV completions are issues of high energy and potentially short distance scales. So maybe those two motivations are related, maybe they're not, we don't know. The other reason to think about why it's interesting to modify gravity, or to think about modifications of gravity, even if you're sat here listening to me talking and you're like, I don't care, Claire, I'm just happy to fine tune it, and that's enough, that's good enough for me, which, you know, is you know, if you're happy to do that, that's fine. I think, yeah, even if that's the approach you're taking to the cosmological constant problem, it's still interesting to think about modifications of gravity because they motivate us to go out and compute what new phenomenology we could be looking for, right? We're at this point in time now where we're about to have a kind of increasingly deep and broad and precise data set of what our universe looks like on the very largest scales, what the distribution of matter looks like. And if you want to test gravity, those systems are sufficiently complicated that you need something to test gravity against. It's not enough to go and make your observations sort of assuming GR in the standard cosmological model and say, oh, look, everything fits. Because maybe you're missing something, or maybe you're not looking for the right observable. So I think just as a way of even just of checking that general relativity is the right description of our universe, it's useful to have something to check it against. So what do those options for checking it against look like?
Can I ask a question really quick?
Yeah, sure.
Thanks. So if we were to do the same calculation that you showed for the simple scalar with a graviton, would we still get that mass to the fourth dependence?
Oh, that's a good question. Well, okay. The first thing is to say, I don't think I've ever done that calculation. So I don't know if there are any subtleties there that I'm not immediately thinking of. I guess the first thing to say is that if GR is our correct theory, then the graviton is massless. So it's only massive fields that are causing us this problem. But if you had a massive graviton, maybe in addition, so that would be another way. We're going to talk about scalar fields in these lectures, but another way of modifying your theory of gravity would be to say, maybe I have two gravitons in my theory, maybe one of them is massive, maybe one of them is massless.
I think if you put a massive graviton in your theory as well, you would get the same issue that the things would scale like mass to the 4th power.
Okay, gotcha. Thank you.
Cool. Okay, so let's share my screen again. So coming back to our scalar field, we are going to make one of the simplest modifications of gravity that we can, which is the idea that we're going to add in a scalar field. Let's just focus on these first lines for the moment. We're going to add in a scalar field. So again, our scalar field has a canonical kinetic term. It has some potential. We've got our matter fields moving on the metric of space-time as we had before. And the only difference here is that we have added in a function in multiplying the Ricci scalar, which depends on our scalar field. So you can think of this, if you like, as making the Planck mass or Newton's constant scalar field dependent. Yeah, so this is kind of one of the simplest things we can do. Now we have a gravity sector with not just a graviton, but a graviton and a scalar field in it. And we've kind of chosen a very kind of simple way of making those now two fields in our gravity sector interact with one another. Now, one thing that is interesting at this point is that we have a number of choices of ways to write this theory. So one of them is the one I've given you here, but I'm also allowed to do field redefinitions. And you know, there's a question you can ask, which is, can I do a field redefinition to get rid of this interaction between my scalar field and the Ricci scalar? And what is interesting is that you can. So the language that we use to talk about this is that these are two frames, choices of frame to describe our theory. So this is known as the Jordan frame, what we've started with here. But if we do two field redefinitions, one is that we define a new metric, which is just this a squared function of our scalar field times what we had previously as the metric of our space-time. And if we define a new scalar field, phi tilde, which is related to our old scalar field in this slightly complicated way, then I can completely equivalently write the theory I had here in the top line as this theory that I have in the bottom line on the page here. So now I have an Einstein-Hilbert term, so a sort of standard gravity term in my action, if you like, for my tilted metric. I have, again, a canonical kinetic term for my scalar field, a potential. It's not exactly the same potential that I had before, but, you know, that's fine. I've got a potential for my scalar field. And my matter fields, sorry, add those in. Well, they were moving on our old metric, but now if I want to write that in terms of g mu nu, then I just have, well, now I have a to the minus 2 of phi times g mu nu tilde. Okay, so there's no magic here. Literally all we've done is field redefinitions. And physics definitely should not change if we do field redefinitions. So the physics of the first theory should be the physics of the second theory. But what it looks like in the second version of what I've written down is that we have, in fact, not a modification of gravity at all. Here it looked like I've modified gravity. I've got a scalar field dependent Planck mass. I've got a mixing between my two fields in my gravitational sector. Now, after doing the field redefinitions, I have standard gravity, what looks like a matter scalar field, right? This is not interacting directly with gravity. And now I just have that my matter fields are moving not on kind of the the metric of that is coming in the Einstein-Hilbert term here, but on some combination of phi and g mean u. So if you were to write this out, what this theory in this picture looks like is standard gravity plus a fifth force, a scalar field mediated fifth force, but a fifth force mediated by just some new boson in the matter sector. So this is kind of where we start to see that even our definitions of what is a modification of gravity and what is new matter in our theory, it's kind of an arbitrary distinction. Sometimes, and this for sure happens in theories of dark matter and modified gravity as well, people get very hung up on, is this a modification of gravity or is this new matter? And I really think that's misleading, because very often you can recast your theory in a way that makes the new physics kind of look like one or the other. Not always. There are some ways you can add new physics into your theory that is very clearly like there's no way gravity could mimic this, or this is not looking like a new field. But I think what is important here is, what fields do you have in your theory? How do they interact with one another? What are the observables, rather than arguing about whether this theory is a modification of gravity or adding new matter into your theory. I should also say, just as an aside, I'm not going to work through this calculation for you, but you can actually write this theory as something that looks like even more of a modification of gravity. And that's, again, an equivalent third picture, which gives you the same physics, which is that for specific choices of A and V, actually, this theory can be written as what goes by the name of an F of R theory of gravity. This is sort of as an aside. So if the Einstein-Hilbert term is not, as we saw down here, not just R, but maybe some function of R, it turns out that when you write down the equations for motion for that, you get higher order derivatives of your metric. That introduces new degrees of freedom. That new degree of freedom turns out to be a scalar field. And if you write that scalar field explicitly, you get an action that looks like this for, as I said, for specific choices of A and B. So yeah, that really is kind of really looks like a modification of gravity. It's not immediately obvious that we are actually adding new fields in here, but they are secretly there, hiding in the higher order equations of motion. Okay, so in the last, what do I have? Just 10 minutes or so. Just very quickly want to talk about the two ways that we have of using this kind of scalar field to drive the accelerated expansion of the universe, to kind of give us the physics that looks like a cosmological constant. Now, one of those is quintessence. So this is the idea. This is the sort of, if you like, the less ambitious option, which is that we say, I'm going to set the true cosmological constant in my universe to 0. All of those contributions from phase transitions and from the vacuum energy density, I'm going to invoke some new principle that says they sum exactly to 0. And then I'm going to look for the physics that can give me the small cosmological constant that we observe to drive the observed accelerated expansion. So in some sense, this is kind of skipping the difficult part of the problem. But nevertheless, kind of it's interesting to see how it works. So again, we have our scalar field. It's got a kinetic term and it's got a potential. And we can write down its evolution equation, and we can compute its energy density and its pressure in terms of of phi dot NV. And we can see that we will get the equation of state that we wanted, which was rho equals minus p, if, or in the limit where our phi dot squared is much, much smaller than v of phi, okay? Because then the v of phi terms dominate over here, and we get an equation of state equals -1. So that's fine. That's a slow rolling regime. That's something we're kind of familiar to with inflation. It's the same kind of conditions. We have different energy scales in the problem, but that's fine. And you can get this behavior either because this evolution equation is becoming dominated by the Hubble friction term, and the field just kind of freezes on the potential, or because the field is settling into the minimum of its potential here.
I have a question.
Mm-hmm.
Is it important that our equation of state is exactly -1? Because this approximation wouldn't give us exactly -1, right?
Right. So it's becoming increasingly clear from observations that the equation of state that we see in the oh, actually, I think I have a slide for this. Actually, let's bring that up to answer your question, rather than me waving my hands. Right. So this is the picture. Top left is the picture that we talked about before. This is the fraction of matter that looks like a cosmological constant, and the fraction of matter that looks like matter. But what we have in the right-hand plot is asking what does our current data tell us about the equation of state of our universe. So this is just a simple parametric parameterization of our equation of state, which is saying, okay, I'm going to assume that the equation of state, for whatever reason, is a constant plus a term that depends on the scale factor of the universe. Okay, so that's not coming from fundamental principles, but that's just saying, what does the data tell me if I assume that it has this form? So that's what's plotted here on the right hand side. So W0, so if we assume it's constant, then WA equals 0, and we're sitting on this horizontal dash line. And a pure cosmological constant, so W0 equals -1, would be this vertical dash line here. So the cosmological constant sits at the intersection of those two lines, and you can see. So this is a combination of Planck CMB data, baryon acoustic oscillations, supernova, register space distortions, weak lensing. So really kind of throwing all of our cosmological data at this problem. And certainly that's consistent with a cosmological constant. There's freedom. It's not the only possible choices of W0 and WA that are consistent with that. I should say, actually, this is a slightly old plot. Actually, there's now data from DES, which actually gives even tighter bounds on this. So the observational data do really seem to be kind of homing in on if at least with a sort of simple parameterization like this, that W0 is equal to -1. But there is still some wiggle room for that. But yeah, it looks like if we're gonna go back to these sort of simple quintessence models, it does very much look like you have to have W pretty close to -1. So you would really need your scalar field to have stopped, really stopped evolving to match the observations.
Okay, that makes sense. Thank you.
Okay, but as I said, quintessence models, while they're kind of good simple models for matching our observational data, they don't really attempt to address the kind of the cosmological constant problems that we've been talking about. As you can see, we've introduced a V of phi that's going to have exactly this problematic contribution to the cosmological constant that we've been talking about. So we really haven't. We can answer the question
Quintessence models are the answer to the question, why is the cosmological constant not 0? They don't really answer, why is it not enormous? And so the other approach that we can take to trying to answer that question, trying to be a little bit more ambitious, is known as self-acceleration. And this is where we come back to our, sorry, I'm just looking for a previous page that we talked about. Our scalar fields that was non-minimally coupled to gravity. Now, remember, we talked about these two equivalent pictures. And I said, just field redefinitions, physics is the same in both pictures. And that's true, as long as you do your calculations carefully. But that means that, for example, if you're computing in this first picture, that you have to be careful that you're not making the assumption that Newton's constant is constant, or that the Planck scale is constant in your calculations. The equivalent kind of assumption down here is that if in this picture, what you find is that the masses of your matter particles become dependent on the scalar field. So your masses are not necessarily constant during a cosmological evolution. So if you're doing a calculation, making that assumption, so if we do a calculation where we assume that the masses of our matter particles in our universe are constant, and we think we're living in kind of this extended gravity theory, modified gravity theory, then we're really doing the calculation in one particular choice of frame. Sorry, if we're assuming our matter fields are constant, we're doing the calculation in this frame, where the scalar field is not showing up in the matter action. Now that's interesting, because that means that we're really computing our cosmological observables in one frame, in the Jordan frame. So that's what I'm indicating with this subscript J. But that is related to the Einstein frame through this redefinition with the scalar field. So what the idea of self-acceleration is that the cosmological constant is large for one of these metrics, so say for this one, but the evolution of our scalar field is such that the metric that I see in the universe, the kind of metric with which I'm doing my calculations, if you like, doesn't see that large cosmological constant. It's hidden by the evolution of the scalar field. Okay. So that's the idea of self-acceleration, and as I said, it's kind of it's a more ambitious way of trying to solve the cosmological constant problem with a scalar field. It does require you to have these to have a non-minimally coupled scalar, for example, in your theory, and these two pictures. Whereby you have to be very careful with your calculations. The other thing that it means, just to say, and this is a point that we'll come back to tomorrow, is so we've got our two scale factors. Which way around are we? Sorry, let me check. I don't say this the wrong way around. So we said, right, we want. Yeah, if our Einstein frame scale factor is not accelerating, that means then, sorry, I'm rushing because I'm aware that we're coming up to half past, and maybe I'm not being clear here. So this equation has come from thinking about the Friedmann equations in our two frames. Okay. So if our scalar fields are related if our scale factors are related in this way, depending on our scalar fields, we can compute the Friedmann equations in both frames. We find that the scale factors are related in this way. And as this is just, I guess, another way of kind of explicitly writing out the obvious point, which is if I want really different physics to happen,
So if I want one of these metrics to be accelerating and the other one not, then I have to have some serious evolution of my scalar field. Like my scalar field can't be approximately constant and have this kind of different behavior between these two metrics. And so that's where some of the problems for self-accelerating models or theories come in, is that you really have to have a significantly evolving scalar field in order to do this. And then maybe on the theoretical side, you run into problems that maybe your field has to evolve kind of through Transplanckian field values, or yeah, maybe it's tied to some other observables that you don't want to change so much during the history of the universe. So it's not, whilst it's a kind of exciting approach to think about solving this problem, it's not without its own issues. Okay, so I am going to stop there for today. What we're going to do tomorrow is to look at 2 example scalar field theories that try and solve these problems in a little bit more detail. We're going to talk about how they do or don't drive an accelerated expansion, and we're going to talk about come back to this issue of whether they can be in agreement with our very good tests of gravity. Yeah, so that's what we're going to do tomorrow. Yeah, it's been very nice to talk to you this morning, and I'll stop there.
I know we're out of time, but can I ask one last really fast question?
Sure.
Thank you. On this self-acceleration, is the appeal of it that it kind of gets us around this fine-tuning issue?
Yeah, so the appeal is, so it depends on, so I've obviously just given you the idea of the self-acceleration. It depends on the details of the theory, the fuller picture of the theory, whether it really solves the fine-tuning. I guess the appeal of it is that it doesn't require you to invoke some unknown principle to say the vacuum contribution to the cosmological constant is 0. So a quintessence model does that. It says, I don't know why it's not huge. I'm going to assume the true value is 0, and then introduce a scalar field to explain why I get this small cosmological constant, that is this cosmological constant, effective cosmological constant that is small but non-zero. But that's skipping over the hard part of the problem potentially. Whereas self-acceleration is kind of trying to tackle that head on and saying, well, maybe in one of my metrics, the cosmological constant is huge. But in my other metric, because of the evolution of the scalar field, that's masked and it looks small. So there's still the potential for fine tuning there, but it's at least addressing the full problem.
I have another question.
Sure.
Regarding the equivalence of Jordan and Einstein frames, because they're related to conformal transformation.
Mm-hmm.
So for me, the physics they describe should be the same, but somehow people only work with Einstein frame. They call Jordan frame non-physical. So that confuses me a bit.
Yeah, I think this is another common misconception that I would really like to dispel. If you're doing a classical calculation and you're careful, you should get the same observables whichever frame you calculate in. So one is not more physical than the other. When people say this is the physical frame, what they mean is this is the frame in which the assumptions that I would like to make to do my calculation apply. So as I said, maybe you want to assume that the particle masses are constant, so you can do thermodynamics in the standard way. That then chooses a frame for you. The slight caveat is when you come to quantization, you have to make a choice about which frame to quantize your fields in, and you don't necessarily, because the fundamental degrees of freedom look different, are mixed between the two frames, you might get slightly different answers depending on how you do your quantization. So there's a slight caveat there, but that's not what people normally mean when they talk about physical or non-physical frames.
Thank you.
Okay, thank you very much. Well, thanks again, and see you tomorrow then. Thanks.
Yeah. Yeah, cool. See you tomorrow.
And do feel free to email me or message me if you have any more questions.